I'm just going to hit record. The reason why I'm going to have a lecture on Monday is because if I don't do it, I need to do it some other time. And so for me, Monday is as good as any day. Okay, hello, Junsheng. So let me stop that poll. This is a tutorial about the deeper understanding. So what I'll try to do is to look at some of the harder questions in the calculus and algebra. In previous tutorials, I already looked at quite a few questions from the algebra. So I thought today we could do some more algebra questions and some more calculus. But of course, you can direct me. We can talk about whatever you want to talk about. So if there are any particular things you want to talk about, then you can ask me in the chat. I'll just see if I can. Yep, everybody can share their videos and their audio. So let's have a look at some of the PDFs that we have here. So let me share my screen with you. So I might look at some algebra questions first. So you can see these are sort of where the H questions are. So these are the harder questions. So I thought we could do a couple of these and then maybe move over to some of the calculus. So let me know what you're thinking in the chat. Happy to take your comments or your questions or your feedback. So let's have a look at 43. 43 involves this line here, and you're asked to show that that line is contained in the following plane and is parallel to this plane. Okay, so I don't think that this is a really difficult question, but maybe some students are not sure where to start. So so we can have a look at this. Okay, all right. So before we do that, let me just show a picture of what's going on here with GeoGebra. So let me just move that over here. Okay, so here is GeoGebra. As you know, I like GeoGebra because it's really simple and easy to use. So there's the three-dimensional space. The gray plane is the XY plane, and the blue axis, I think, is the Z axis. So let's put in our line. So that's what our line looks like in three-dimensional space. And let's put in our plane. And you can see, hopefully, that the line is contained within that plane. So just from a picture, we can kind of say, well, yeah, it looks like it's true. So that's fine. And then for the other plane, in the second part of this question, you can see, well, it's not contained in it, but it's definitely parallel. Okay, so let's work through that question and we can have a look at how to solve it. And if you've got suggestions on which questions I should do, then let me know. Yeah, this is PlushyCam. Okay, I'll let you know. All right, so let me go to my document camera. All right, so this is question 43. All right, so consider the line L. And here the parameter is t. Okay, and the first part of this question involves the plane. So how do we do it? So let's call this plane P, and it's a Cartesian form. Okay, so can anyone on the chat think up a strategy? How might we show that this is contained in this plane here? Can anyone let me know what strategy might be helpful here? Let me know. Smash that chat button. Who can tell me? Come on, there's 20 people here, including me. So we should be able to maybe put our brains together and come up with a strategy. Who can tell me? Don't be shy, people. Don't be shy. Any idea? This is the idea. So what strategy might we use? Well, Brendan, interesting suggestion. Change the plane to a vector form. Convert to parametric. Ooh, interesting. Keep the suggestions coming, people. They're all fine. They're all fine. So I think if you change that to parametric form, then you would compare, the points here with the parametric form. But there's even easier way. There's even easier way. But what you're saying is good. So from here, you know that x equals 2t, y equals 1t, and z equals 3t. What you can do is substitute in here, here, and here, and see if it adds up to 0. Okay, so what you're suggesting in the comments are all good, but this is probably the fastest way. So from L, we know that x equals 2t, y equals t, and z equals 3. And we substitute that into p. So the left-hand side, we want that to add up to 0. If we know that that's true, then every point here has to satisfy this. Okay, so 5 times y is 5 times t, and that's 3. 3t, sorry, 3t. Okay, because z equals 3t. So what have we got here? We've got 8t minus 8t. So the left-hand side of that is equal to the right-hand side. So what we can conclude is L lies on P. Yay! Great. So you can see once you know how to do these questions, it's actually not very hard. It's just that some students, they're not sure where to start, or they make it very complicated. And Brendan, Oliver, and Anna, your comments are all correct, but they would probably take more time than just doing it this way. Okay? All right, what about part B? Let me show you again. So we know that from our picture before, show that this is parallel to this, okay? All right, well, again, there's a few ways you can do it. And I'm going to show you a quick way to do it. You may or may not have seen this in the algebra lectures, but I think it's important anyway. Okay, so let me do this Q plane with here, and I'll show you how to do it. Okay, so let me go back to my document camera, and I'll call this plane Q. Okay, so now we've got these points on these lines. Is this line parallel to this plane? Oops, excuse me. Okay, so We could convert that to parametric form, parametric vector form, and compare the parallel vectors to this. Are they parallel to that? But there's an even easier way. Okay, so if I have a plane and I take the coefficients of x, y, and z, that gives me a normal vector to the plane. Okay, so let me know if you've seen this in lectures. If you haven't seen it yet, you will see this. Okay, and this is just a quick way of solving this problem. Okay, so in this setup, what is a normal vector going to be? Well, it'll be 3, negative 3, 1. Okay. Okay. So we know that this vector over here, that's the line, that's the vector that's parallel to this line. That's a vector that's normal to this line, right? What you can do is show that this dot product is 0. Now, again, you might not have seen dot products yet in your algebra lectures. So let me just show you, right? Okay, to compute the dot product, it's that times that plus that times that plus that times that. That's how you do it. So if you add those up, you get 0. Okay. So what does it mean? It means this vector and this vector are perpendicular. So that vector has to be parallel to every vector in the plane. Okay. I just took the coefficients of x, y, and z. Okay, so here's the general case. It's a good question. Okay, and you might not have seen this in lectures yet, but you will see it. Trust me. Okay, so if I have 3x minus 3y minus 1z equals 2, the normal vector is just the coefficients of these. Okay, so that's a very easy way to do it. Okay, and there is a geometric justification for that you will see in lectures. It's a good question. Now, of course, you could convert that to parametric vector form, right? So how might that work? Let's do that, because you like, I think that might be the way that they want you to do it. So actually, let's just spend a little bit of time on that, okay? Because it sounds like you haven't seen this yet in lectures, but you will see it. Trust me. So alternatively, let's go up here and we'll let, I'm going to let, I've got to introduce 2 parameters, right? And I might let x equal lambda and y equal mu. That way I don't have to do any divisions, okay? But you can do it lots of different ways. So we're going to get something like z equals 3x minus 3y minus 2. So I've just rearranged the equation for q. Yep. And so that's going to be 3 lambda, oh, sorry, this should be mu, minus 3 mu minus 2. So I've got this, this, and that. I can write that as a column, and then I should be able to get my parametric vector form. Okay, I can break this up into 3 parts. Okay. So now what I would like to do is to compare these vectors with our vector v. Okay, so okay, and you want to, I guess you want to show that that these vectors are parallel to this vector v. Okay. Or you can show that v can be made out of a linear combination of these things. I think that's also another way of doing it, right? So if you had 2 lots of that plus 1 lot of that, right, then you know that's enough. Okay, so you can see how actually this method over here is actually much quicker than that. Okay, yeah, you can see that 2 lots of that vector plus 1 lot of that vector equals v. Okay, all right, that's probably enough for 43. Let me go back and share my screen again. Okay, so 44 is an interesting one. It's very similar to the ideas of the previous questions. Let's do 44 quickly, and then we might switch over and do some calculus, because I think some of the calculus questions are pretty interesting this week. So let's have a look. Find the intersection of this line with this plane. So you would just let that equal x, that equal y, and that equal z, and put it in there and find t. And for this one, very similar. Okay, so let's do those, and we can discuss it together. Right, let me share my screen with you. Yep. All right, so consider the following line. Yep. So you can see in this one, it's like it's in parametric vector form, but everything's together. Okay, and t is the parameter. So they haven't split this up into, well, a point plus t times a vector. Let's write this as our plane P. Okay, so what we can do is this and this intersect when their equations hold, and so we take this substituted in and find a value of t. Okay, so sub L into P via, so this is very similar to what we did before. That's a Z, believe it or not. Okay, so we'll go in here, we'll replace X with 2 plus T, Y with 3 minus T, and Z with 4T. And we want to find a T, okay? All right, so it's 2 plus T, plus 3 minus T, plus 4T equals 16. And we want to solve for T. All right, once we've solved for T, we can go back and take that value, put it in here, and we can get a point. Okay, so we're going to get 4 plus 2t, 9 minus 3t plus 4t equals 16. So 13, so we're going to get 3 on the right and 3t on the left. So you can see t, the value of t that makes this and this intersect will be t equals 1. All right. So let's take that value of t, put it in here, and find the point that this is associated with when t equals 1. All right. So let's call it, what should we call it? Let's call it C. Okay, so when t equals 1, x equals 2 plus t. Y will equal 3 minus 1, and z will equal 4. So again, not a difficult question algebraically. It's just knowing that you can take these components and substitute them into the other equation to find the intersection points. And to do that, it's helpful if you know the value of the parameter at that point. Okay. So let's do part B. Part B is very similar. So let's just write this out. So there's more information here. So this will intersect with the following plane. When x, you substitute for x in there, substitute for y in there and z, and you find a value of lambda. Okay? So that's the x part going in from up there. The y part is 2 minus 3 lambda. The z part is 3 plus 4 lambda. And just like the previous case, we want to solve for lambda. Okay? So I think according to my calculations, you should check this. I think lambda equals 2. And so the point of intersection, good one, Anna, thank you, is, so when lambda equals 2, x will be -1 plus 2 times 2, y equals 2 minus 3 times 2, and z equals 3 plus 2 times 4. Okay, so I think you're going to get something like 3, -4, and 11. Okay. Yeah, that looks right to me. So there's your point of intersection from the first part. There's your point of intersection from the second part. Okay, sweet. Yeah, that's great. Good job. Okay, let's do some calculus. Okay, let's do some calculus. Before we go there, let me just show you one more thing. I think earlier in the week, somebody asked me to solve these questions, right? So these are more long rather than difficult, right? These are, yeah, Shub, these are in the course pack. Okay, Shub. So this is it, right? So every week we do questions from the different course packs. Okay. So when you say the type of questions in the lecture notes, I'm not sure really what you mean. Let me know what you mean. Okay. So these are all the questions in the course pack. All right. So just before I switch to calculus, yeah. So these ones look quite tricky, but all you're doing is you're trying to write these and in terms of x, y, and z and eliminate the parameters. Okay. So it's not hard to do that because the equations for these questions are not too difficult. Okay. So in this case, z equals 4 plus 6 lambda. Right? You isolate the lambda and you put it into the middle equation. And then you isolate the mu and you put it into the first equation. And that'll give you the Cartesian form. Okay? All right, let's switch over. Let's switch over. Now, I know most of the questions are around chapter 2 for this tutorial, but I think I've actually done a lot of those. And we've already done this stuff in calculus lectures last week. So what I thought we could do is do some of the harder problems, maybe like this one here, using the IVT. Okay. Shub, I don't know. I think you should have those questions. You should have them for algebra. Yeah, I mean, you can't put every question from every type of question from the course pack in the lectures. There's like hundreds of questions, right? So occasionally you'll see something in the course pack, like these sort of questions that you might not have seen exactly in the lectures. Okay. So let's have a look here. The IVT. Are you down with the IVT? Yeah, you know me. So here's an interesting one. Suppose that f is continuous and on this set. So it's a closed and bounded set, right? 0, 1, it's a closed set. And the range of f is a subset of that. By using this function, prove that there is a real number c, at least one real number, such that f of c equals c. So students find this very hard because they're not sure where to begin or how to use the intermediate value theorem. So this is quite a difficult question, okay? But when you see it done, it's actually not too bad. So let me share my screen with you and we can have a look at what's going on. All right, so this is question 7 from chapter 3 for the calculus. Okay, so let's f be continuous on this, and the range of f is a subset of 0, 1. So what this funny looking symbol means is this set is a subset, or it could be equal to this interval here. Okay, that's kind of all the information we're given regarding the range. Okay, so the domain of F is this set. The range of F is no bigger than this set. Okay. Furthermore, we are told that. Oh, actually, we've already just said that, right? Okay. All right. So the idea here is to use the intermediate value theorem with g of x to be this difference here to show f of c equals c for at least one value of c in this interval. Okay, so this is not an easy question. Okay, but we can basically use this information here to help us out. Okay, so how do we do it? Well, I am glad you asked. So we want to show that that's equivalent to showing there's at least one c such that g of c equals 0. Okay. It's equivalent to showing g of c equals 0. So let's work with this g function and see what happens. Okay. All right. So we know from this the range of f is between 0 and 1. So for every x in this interval, f of x is going to be between 0 and 1, right? And we also know that x is between 0 and 1. So if we combine these inequalities with this inequalities, we can have the following, right? So what can we say about this? Well, remember this is just g of x. Okay. Well, what do we know about g of 0? That is f of 0 minus 0. And g of 1 is f of 1 minus 1, right? Now, f of 1 minus 1, we're just looking for signs here now, right? So f of 1 minus 1, because the biggest that f can get is at 1, right? So that's got to be less than or equal to 0. And this, f of 0, the least that can be is 0. So that's got to be greater than 0. Oh my goodness. So g of 0 is greater than or equal to 0. G of 1 is less than or equal to 0. So what does the IVT say? G of 0 is greater than or equal to 0. G of 1 is less than or equal to 0. There must C, there's at least one C such that g of c equals 0, and that is equivalent to showing that. Yeah. Okay, so it took me a while, right? I had to think hard about these inequalities here. But the important thing is we found a point where g was greater than or equal to 0. We found another point where g was less than or equal to 0. Yeah, it's a hard, it's not an easy question, Shub. Okay, so we're only using two things here. The input's in there, the output's no bigger than that, right? Showing that is equivalent to showing that. Okay. Yeah. So what does this mean? It means for every input, the output's between 0 and 1 of f. Yeah. Okay. And so let's try to apply the IVT to this function. So g of 0 is that, which is that minus that. Now, f of, this is true for all x, so f of 0 has to be greater than or equal to 0. If we put in x equals 1, this minus this gives us that. This has got to be less than or equal to 1 because look at that. Oh my goodness. Okay. Oh, I guess you can say that's equal to 0, right? Okay, so g of 1 is less than or equal to 0. Maybe that's a bit more correct. Yeah, Anna. And so greater than or equal to 0, less than or equal to 0, you know, g is continuous. And so you can apply the intermediate value theorem. Yeah, it's right, Anna. And if the range was bigger than the domain, then you wouldn't be able to apply this in the same way, right? So that's a good question. How do we get 1 minus 1? Sure, f of 1 is less than or equal to 1. Okay? Yeah. Okay? So for every x, this is true because it tells you like that's really what this means as an inequality. Okay, cool. So it sounds like you're with us now. All right, so that's a very hard question. And don't be too worried if you're looking at that and going, well, I could never think of that. Okay. All right. Don't worry too much about it because you know, sometimes it's actually easier to see the solution first. Yeah, I would have never got that. Oh, me neither. But now, because you can see where it's come from, yeah, you know the score now, which is great. Okay. I don't know. Those kind of questions make me angry. Oh well, sorry. Kevin, it's hard to say. If it might be true, but the method of solution probably wouldn't work. You probably couldn't use the intermediate value theorem. Okay, it's a good question. Yeah. So maybe, you know, if you definitely know that the range is a subset of the domain, then the intermediate value theorem can help you. If it's not true, the conclusion still may be true, but you just don't know. It's because, you know, the intermediate value theorem relies on sufficient conditions. Okay. Let's do another one. Let's do another one. Okay. All right. Let's talk about max-min theorem. Okay. So the maximum minimum theorem is an amazing theorem. It's really simple, but we can use it all the time. And these kind of questions here, it's not a H question, but it's designed to help you think about your functions. Okay, so let's have a look at some of these functions. So the first question is, determine whether or not f has a maximum on the given interval, okay? So does this function have a maximum value? Who can tell me in the chat? Who can smash that chat button? And does it have a maximum on the interval? Yes or no? Let me know in the chat. Okay, Anna, Kevin, Ichan, Oliver. Yep. So the next question is, how would you justify why does it have? How do you know it has a maximum? How do you know? Yeah. So yes, it's a closed interval, right, Chen? And as Brendan and Oliver have pointed out, it's also a continuous function. It's a continuous function because it's a polynomial. It's a polynomial. Okay, so you could apply the min-max theorem to that function, and you definitely know that it has a maximum value. Okay, what about this one? Does that have a maximum value on the interval 2, 4? Does that function have a maximum? Let me know in the chat. Who can tell me? Does that function have a maximum? Who can tell me? Brendan says no. Anyone else want to say anything? What, Brendan, why do you think it doesn't have? Oh, okay. Okay. So no, yes, yes. Well, definitely this is a closed interval and this is a function that is continuous on that closed interval. So yes, this would be a yes. Okay. Let's have a look at C and D. I might go to GeoGebra and pull that out and see if we can do some graphing. Okay. So I'm just going to put this into the thing. So have a think about it. I'm going to just put this, typing this into GeoGebra now. Oops. Hang on a sec. Okay, all right. So I'm just going to slide my GeoGebra over there. So let me share my GeoGebra with you. Okay, here it is. Now, does that function attain a maximum for x strictly between -3 and +5? Maximum? Who can tell me? Who can tell me on the chat? Does it achieve its maximum value? Correct. Correct. It does not. What about minimum? What about a minimum value, people? Does it achieve its minimum value? Yes, but you cannot apply the MVT. So it does achieve its minimum value, but you cannot apply all the max theorem. Okay, let me put that in the chat. Okay, so it does achieve its minimum value, but you cannot apply the max-min theorem because the conditions of the max-min theorem do not hold. Okay. What about the other? Oh, what about the other part of this? There's another one here. Yeah. So let me do this one. Yeah. Well, actually, I can just change that now. So this is the next part of the question. Okay. Yeah, it's a good question, Kevin. Good question. So Kevin, if we write something like this, it means okay. That's what you mean. All right. So for this one, does this function achieve its maximum? Who can tell me in the chat? Is there a maximum? Maximum. Is there a maximum there? Yes. What about a minimum? Does it achieve a minimum? No, it does not achieve a minimum. Okay. So again, the MVT doesn't work here because this is not a closed and bounded interval. Okay. Yeah. All right, everyone. So the max-min theorem, I think, is fascinating. The intermediate value theorem, the IVT, is also very interesting. And they both, well, the intermediate value theorem says it's like an existence theorem. It tells you something exists, but it doesn't give you the precise value of it. It's pretty interesting. All right, folks, we got a couple of minutes. What would you like to talk about? Do you have any particular questions or comments or feedback? Remember, summertime in Sydney starts on Sunday. So if you want to come to Monday's lectures, you need to get up an hour earlier. Okay, you need to get up an hour earlier, which is not great, right? No, I want to sleep in. I don't want to get up. Me neither. Oh, you died. Look, I totally understand that. And of course, for Monday's lecture, you don't have to join us, right? Yeah, Naomi, that is a great question. So for lab tests, lab test 1, lab test 2, you will get some practice tests to practice with. And the questions are usually the same or very similar. Okay. What's your question, Shub? I know. So summertime will start here in Sydney from Sunday morning. So I know it's going to be a super early start. Early start for Shub. So if you want to join us, feel free. Correct, Kevin? So you'll have to get up an hour earlier. I know, it's crazy, Shub. It is super crazy. But of course, we'll be recording everything, and yeah, it'll, you know, there'll be recordings to watch as long as the technology doesn't fail, right? As long as the technology doesn't fail. The prep materials will be in it'll be in Mobius. Okay. So Ben, if you go to the live lectures, there's a little window up the top and it's got 3 lines on it, and you press it and it comes up with live recordings. Okay, so you go to the same link, but you go up to the top left-hand corner and it'll say recordings. Okay, so the same place where you see live lectures. All right, folks, if there's no more questions, I've got another tutorial in about an hour. No calculus lecture on Friday this week, but maybe I'll see you Monday. If not Monday, I'll see you next week sometime. So greetings of the day. Have a great day. Yeah, enjoy. And hopefully I'll see you next week at the correct time. Okay, thanks, Ben. Thanks, Archen. Kevin, Louisa, Shub, thanks, bye. Naomi, Anna, Oliver, Ben. Bye, everybody. Thank you.